Here, let's continue to take a look at the sections, and this is about the Mohr circle. And Mohr circles is the very important topic. And if you learn this tool well, that will save you a lot of time in calculations in determining the many problems regarding the analysis of the stress. So these sections is very important. So let's first define and introduce what Mohr circles is. Basically, here from the previous sections, you know you have learned we have the equations for taking care of the transformation of the stress and normal stress in both x, y prime direction and strain stress. Okay. So for those equations, for example, if you combine normal stress and the strain stress equations together, okay, so if you combine both things together and take advantage of the trigonometry cosine square of any angle plus sine square of any angle equal to 1, you take this advantage actually by doing a little bit kind of the derivations, then you could find, you should be able to find is this equation here. Okay, combining the two equations together, you will find this one. Okay, so here we have two parameters, and first parameter is this one that called the sigma average, and this one in the derivation we found that number is this, and the second parameter is r, okay, or r squared. R is simply equal to defined by this. So from the two parameters you can see those numbers are given. So basically once we have a given status of the stress, you should be able to directly determine the two parameters. Okay. On the other side, if let us look at this equation in more details, and actually you can find this equation is equation for describing a circle. Describing a circle in a very particular coordinate, and what kind of coordinate? In terms of compared to our circle equation in xy coordinate system, we have x minus c squared plus y squared equal to r squared. So for this circle, basically describing is in terms of xy coordinate and the center at C with the radius equal to r. Okay, so now you compare to this our understanding. So that means this is our coordinate corresponding to this. This is our coordinate corresponding to this. So in such a particular circle actually can be shown in the particular coordinate system. This is our horizontal axis, so here using this one, and this is our y vertical axis, so we use this one here. Okay, so basically let me erase this one. So basically this is the circular equations. The circular equation described in such a particular coordinate systems here. Okay, so here again we combine the two equations we can obtain is a circular equations, and you may ask, can I combine the two equations? Yes, you can. If you combine the two equations, and again you will obtain is the same the equations, but will get a sigma y prime, because right now you're using sigma y prime, and minus average and square plus tau x prime y prime square equal to r square. Okay, so now if you pick up the two, then basically you have the coordinate like this one. So in general, we like to describe is here the people like to use symbols, but basically here let me put into more literal the literal description. Basically this horizontal axis is the axis for normal stress. Okay, that will be more general, and the vertical axis is the axis for strain stress. So basically here the circular equations is drawn or is illustrated in a coordinate system which defined by two axes. One is the normal stress axis, one is the strain stress axis. Okay, and such a circular equation describing a circle. This circle is called the Mohr circles. Okay, Mohr circles is then simply is a very concise integrated descriptions of the three equations in a particular coordinate system. What kind of coordinate system? The normal stress axis integrated with the shear stress axis. Okay, so with such an information, keep that in mind, then we begin to exercise how to construct a Mohr circle. So here I highlight the steps here, and let's go over the steps in general, then we will follow up with a few numeric examples here. So the first one you draw is to define the coordinate system. Okay, the horizontal axis is the normal stress, and the vertical axis is the shear stress. Okay, then you begin to locate the center and radius of this Mohr circle. Okay, so the center is determined by average. Okay, so for example here we locate the center here, and that one has the location is determined by this average. Okay, and here I would like to remind you the Mohr circles have the center always on the horizontal axis. The center of the Mohr circle is always on the sigma axis. Keep that in mind. Okay, now we in turn we determine the radius. So basically radius, you take up this equation here, and once you determine the radius with the center with a radius, and you can form a circle. Okay, that is the easy way, and that is the quickest way to formulate the circle here. Then once the Mohr circle is built up, then we need to locate the two particular points. The two particular point is called the x point, and the other one is y point. Okay, and the x y points representing is this. I highlight here the x point have the coordinate, the two coordinate, and that representing is a stress in the x plane. And what I mean here, so for example this is our axis, so basically this is a plane, then we call the x plane. That plane has the normal direction to the x directions here. So in the x plane we have two components. The first component is the normal stress, so we put onto the first coordinate, and the second component is shear stress, we put into the second coordinate. Okay, so what is the y point? The y point representing is the stress in the y plane, so this is our y plane here, so that is the y plane. Okay, so in the y plane we have the two stress component. Y is the normal stress, which is sigma y, we put down to the first coordinate. Then we have tau xy, we leave that into the second coordinate. So that is a way we determine the coordinates of the two particular points, and then in that way we can locate the point in such a coordinate systems, and actually the 2 points must be on the Mohr circle. If not, then your construction of the Mohr circle is inaccurate, and in such a case go back to double check all of your calculation to this point. Okay, so that is the procedures of constructing the Mohr circle, and that should be very easy because here involved is only pure very easy geometry. And then you may ask me, and why we bothers with the step 3, why we want to determine the particular x and y points. Actually the 2 points will serve as a starting point to many important I would say summaries of our learned the principal stresses, principal directions, transform stresses, etc. So x, y, the 2 points serving as a starting points to those calculations. Okay, so again, here this page is very general, and a few information you probably need to memorize is these equations and these equations. And here from this moment onward, I can tell you this probably is the only 2 equations you need to memorize in this chapter. again, once you can manipulate the Mohr circles very well, then these would be the only two equations you need to memorize and to handle all the transformations of the stress problems here. Okay. So now we move on to look at the examples, and I want to kind of show you in details how do we build up the Mohr circle and from that point onwards. Okay. And here we have two examples. Let's look at the first example here. So we are given a status of the stress like this one. So again, we first determine the center of the circle. And again, that is a formula I listed here, and we have sigma y, sigma x, sigma y, and here sigma x equal to 100 and sigma y equal to 300. And again, here you have to take sign conventions. Okay, and if you remember, the normal stresses is tensile for positive, normal stresses compresses for negative. So here the both are tensile, so we take the positive. Okay, and for the determine the radius basically taking up this equation here, and then that is 141 here. So now we determine we have a center at 200, so we draw the the coordinate, and the distance here is 200. Okay, and with the radius equal to 141, so with the center with the radius, then you can get the circle, and to get a circle to make a circle here. Okay, so now we have built up the Mohr circles, and then I'm going to continue on step 3, determine the x point on the Mohr circle. And again, the x point representing is the status of the stress in the x plane. Okay, so this is our xy coordinate, so this is the x plane. In x plane, and we have they're going to constitute the x point. So the first coordinate is the sigma x, and which is 100. The second component is constitute xy. Okay, so xy here, the magnitude is 100 here. Okay, so here I just like in terms of the value, that is 100 here. Okay, now here you look at here, I have the kind of arrow sign here. Let me explain this to you. This is the assigned sign convention for correctly operating the Mohr circle. And this kind of the sense of the rotation, I simply follow up our textbook, and there's quite a few different types of the assigned the sense of the directions, but here I simply ask you to adopt what I'm going to describe, and once you can manipulate, once you can operate these kind of things very well, then actually all of our calculation will be consistent with all other approaches. Okay, so now we're back to let me get more explanations about the direction here. So now we focus on this strain stress. Okay, now the strain stress is 100, pointing direction is kind of upward there. So here this kind of the direction can be explained by this. The strain stress point upward, and that will exert or has a tendency to rotate this stress block respect to the origins in counterclockwise ways. Okay, again, the direction of the strain stress has the tendency to rotate this block in counterclockwise. So that is the way we determine this rotation. So that way I determine the rotation here. Okay, and so in this way I have the sense of the x and we have the x points being determined in this way. Then we can label the x point. So x point has a 100, and such that the second coordinate is in this sense. So the lower quadrant is in this sense. So basically x located here. Okay, now we look at continuously on the y. So before we look on the y, let me erase unnecessary information here to move on here. So for y, again, this is the y plane. On y plane, we're going to constitute the y point. The first coordinate is the normal stress, which is 300. The second coordinate is constituted by shear stress, which has a magnitude 100. And again, this direction of the shear stress has a tendency to rotate this stress element, about the origin in this direction. So I put the arrow like this. Okay, so now this has the y has the coordinate 300, 100. So 300, 100, and then here, because this second coordinate has the sense, so we place it into the upper quadrant here, so like this one. Okay, so now you have successfully using this example to constitute x and y. And one final point to mention to you, and as a final check, so once you label x, y correctly, then once you connect x to y, and that connection will be a diameter of the circle, which means if you would place the x, y point correctly, then their connection will pass through the center. If not, then saying you have something incorrectly done. Okay, so go back to check your calculations either on the Mohr circles or on the identification of the x, y points. Okay, so now let's continue to look at the second example here. So again, we have given this one, and the difference between this and the second example from the first one would be everything is the same, but the only thing different is the directions of the strain stress. Okay, so compared to this one, that's the only thing difference. So using this particular difference, making this particular difference, I simply want to demonstrate the difference between the two circles here. Okay, so here we have the components in the same magnitude. So basically the center just be calculated as we did before. Simply plug in the equation for center, and then we simply plug in the equation for radius. Okay, and because here we're dealing with the same magnitude, so basically the center and radius is the same. So here the circle you draw it has the same as this one. And now we begin to move on to determine the x and y point. So x point, first one, this is the x plane. This is our x plane, and in which we define the x point. The first coordinate is the normal stress, that is 100. The second coordinate is the magnitude, is the strain stress, is 100. Now this strain stress, you can see, has a tendency to rotate this stress block respect to the origin in clockwise way. So that's the direction here. So now with this one, you see this one x point must be up in the upper portion, because we simply adopt this sign. So here we label x 100 and 100, and then that is on the top here. And now we move on to the next one. This is our y plane, and in y plane, that's going to constitute our y point. The first component is our normal stress 300. The second component is our strain stress 100. Now the strain stress has a tendency to rotate this block in counterclockwise, so I put the direction here. So 300 with 100 in the sense, so here 300 with 100 here follow this sense, so that y should be here. Okay, so from here you can see the two examples, the only difference is in the sense of their xy point. Okay, so let me highlight the quantity, erase this one. So from here you can see that's a difference, and hopefully from this example give you more feelings about the Mohr circles. Once we are familiar with the steps of constructing correctly a Mohr circle, then here we are able to study how to use Mohr circles to deal with the analysis of the stress. And here we're going to talk about is the important applications of the Mohr circles. And the first one is, the first important application is we apply the Mohr circle to find the principal directions and the principal stresses here. Okay. So in general, the concept is this. So once you have built up a Mohr circle with the x and y point being labeled, so this basically representing is our given stress informations. Now the principal directions and principal stresses basically is this. Let me change color. Point A and point B. The magnitude of the normal stress, one is sigma max, one is sigma min. The two are the principal stresses. And the reasons, I'm going to ask you why. If you remember our definition of the principal stresses, we define the principal stresses is happening in the direction there's no shear stress. Okay, so in the principal directions are defined as no shear stress. So the only 2 points in the Mohr circle with 0 shear stress component is here, A and B. Okay, so that means the A and B, the 2 points representing the magnitude representing is the principal stresses. And then the orientations is such that with the given xy, and that is representing is our given the stress, the given status of the stress. Okay, so for example like this one, then we're going to begin to rotate. So in the Mohr circle, you can see from this is the xy is the diameter representing our given status of stress. From the given status of stress, and AB diameter representing is the principal stresses. So the transformations between the given and the principal stresses, basically that is the angle to define the orientations. So that is the how to calculate the orientation is pretty easy. You simply find the angle between the given diameter and the diameter for principal stresses, which shown here, that is this angle. And this angle representing is the twice amount of the angle we're going to operate here. So for example here, this is x prime y prime, and this is the sigma p. The sigma p is our principal directions. When we operating in the transformation of the coordinates, and that is angle, when we do the same thing on the Mohr circle, the angle will be doubled. Okay, and here we have profound explanation, but at this moment you simply take it, which means in the real original transformation of the coordinate system, we take 1 theta, and then on the Mohr circle we will take 2 theta. Again, any rotations on the Mohr circle, the angle rotation on the Mohr circle, that will be twice amount of the angle of the rotation in the between the coordinate systems here. Okay. So right now we have identified the sense of the principal directions on the Mohr circle is this one, and that one we also take up the fact that is a double of the amount, so we put a 2 theta p here. So now how can we easily determine the 2 theta p? Then that one, let me erase those informations. Let me show you in details here. So to determine the 2 theta p, that can be very easily done. And by doing this, you can see here I pick up a triangle here. And for this triangle, and you can see this is the R, the side is the radius, okay, and then for example, what is this side? This side is tau xy. So let me rewrite the triangle here to be let us focus here. So this is r, this is tau xy, and this is the angle to theta we're going to find. So from this case, are you able to see and sine 2 theta p equal to tau xy divided by r? And here is we do the things by symbols, but once we have a numbers, we have a values for each parameter, then you should be able to quickly determine 2 theta p. You can take the arc sine, okay, by punching calculators. So in this case, the theta p can be calculated right away by simply using this triangle from the Mohr circle. Good, okay. So that is the kind of general introductions, okay, and then here that is the detailed calculations, and so that is the kind of the give you the sense of the calculation, and then in more details here, okay. And again, you with the build up the Mohr circles, and then here the theta p, and you can utilize again this triangle here, okay. And for this triangle, and you can utilize is what I did before, and or otherwise, let me highlight here, that is a triangle here. So this angle is 2 theta p, and this is tau xy, and earlier I demonstrate you can use sine tau xy over r, or otherwise, and per our formula in approach in textbook, you can determine this distance here. The distance, if you look at this one, basically that is sigma x minus sigma y divided by 2, okay. So either way, if you take up this relation, then basically the 2 theta p and tangent will be equal to tau xy and sigma x minus sigma y divided by 2, okay. So like we did here. So either way, so as long as you have this triangle and pick up whatever the information that is convenient to you, and you simply punch the calculator, and you should get this one. Okay, now the final point is I want to describe is this one. So once we determine the magnitude, and then you can determine the magnitude, and then how to define the orientation. Orientation is this. This diameter is our respect to our given status of stress, and now we identify the sense of rotation is in such way, so that in that way, that basically is a counterclockwise. So when we do the rotation, kind of graphical representation on the stress element, we have from the Mohr circle determine the magnitude using these calculations, and we also determine the sense of rotation by looking at the graph, okay. So in this way, once you have the magnitude, you have the sense, then when you draw it on the stress element representation, you must have this kind of sense here, okay. And now once you have drawn this one, this is the element, so basically this is x, and when you rotate, then x point move to A, or let me call it x prime, and then B, y move to this point, let me call it y prime. So from here, this is our x-axis, this is our x prime axis, and this is our y prime axis, okay. So x prime representing is the point here, that is the maximum 0. Okay, so right now from here, you know that is a coordinate on x prime. X prime representing is the status of the stress in this plane. The first coordinate is the normal stress, so that's reason why here the normal stress maximum is this one, okay. Then y prime has the coordinate minimum 0, and y prime representing is the status of the stress on this plane, so that reason why the first coordinate is minimum, and like this one, okay. So we can look at one example here, and we continue from our previous examples, and we see how can we utilize to determine the maximum, the principal stresses and principal orientations, okay. So from the previous exercise, we know the given status of the stress. We have the Mohr circle and we have a xy representing the status of the stress, and for x point on this one and y point representing the status of stress on y plane here. So that is the given one. So now we know that the principal stresses will be here and here. Okay, and how much that can be written down easily. This one basically is the amount of that one plus this is the radius r. Okay, so maximum simply equal to the average plus r. And what is average? Oh, I forgot that numbers. We can look at this one previously. Average is 200, radius is 141. Okay, let me pick up that number here. So that is 200 plus 141. So this is 341. Okay, and what is the minimum? So this is the minimum. Minimum basically equal to the average minus r. If you look at graphically here, so minimum equal to the average minus r equal to 200 minus 141. So that's a 59. Okay. So here by doing so we determine the magnitudes. Okay. So now we want to determine the orientations. So let me continue on this one. So now to determine the orientation, so here I decide, and there's two options. Let me say, so if you decide go rotating by this sense such that the x will move to here, this point, then we call the x prime, and y due to these rotations, and will move to y prime here. Okay, so basically this is the angle to theta p. Okay. So there's a 2 theta p here. So let's determine the angle here. So let us utilize, let me highlight this triangle. So I'm going to use this triangle to determine the magnitude here. Okay. So for this triangle, let me highlight here. So this radius, maybe you can do this right here. So for this triangle, okay, let's continue. Sorry for the interruptions, and a phone call kind of distract me. Okay, so now we're back to here, and let me utilize this triangle here and to determine the 2 theta p, the magnitude of the 2 theta p here. So from here you can see basically this distance is 100 as determined by the second coordinate. The distance from here to here can be determined by how much. We know the first coordinate is 100, so the 100 is here. So by taking this average is 200, so we know this is 100. So in this case, this is a triangle. So for this triangle, can you see that is a triangle something like this, and this is 100, this is 100, this is 2 theta p. So from here you can quickly see 2 theta p equal to 45 degrees. Theta p equal to 22.5 degrees. Okay, and then also from here we determine the orientation is in this sense. So let me copy in that sense. Okay, so under these situations, then we can draw the orientations. So let me erase this one here a little bit. Oh, I think that's okay. Let me do it. So under this case, the theta p we calculated is 22.5 degrees in this sense. So let me draw that one. So this is our sense, and this is theta p equal to 22.5 degrees, and this is our x prime, this is our y prime. Okay, so in x prime we look at the point, because here we already decide the rotation is in this sense, so x will move to here, x prime, and x prime has a coordinate is minimum is 59 and 0, as we calculated a few minutes ago. So in x prime, that is the normal stress is 59, shear stress 0. Okay, and now this is y, we're rotating in this sense to y prime here. Y prime has the coordinate maximum. The maximum that would be equal to 200 plus and 341, as we calculated earlier. So in y prime direction, we have the normal stress y prime. Okay, that is 341. Okay, and there's a no strain stress here. Okay, so that is the first options of the determine the strain stress. The principal the principal stresses and principal directions. Now I want to show you the second option here. The second option is you can determine, say, if you decide to move x to here, this is called the x prime. So that is the sense of rotation you choose. This is okay as well. Let me call this is 2 theta p, and let me distinguish from the previous one. So let me call it 2 theta p2 here. Okay. So if you choose in this sense, then y will be moved to in this sense to here. That's the y prime. Okay, x prime has the coordinate 341, 0, and y prime has the coordinate 59, 0 here. Okay, and what is 2 theta p2? 2 theta p2 basically is the 180 degrees minus this angle. That angle equal to 45 degrees, as we pick up from the previous calculation. So that is 135 degrees. So in this case, theta p2, the second principal direction, is equal to 135 degrees divided by 2. That is 67.5 degrees. And how about the sense of rotation? Sense of rotation is in that sense. So let me copy that one. It's in this sense. Okay. So under this situation, let me draw that one here. So from here, the sense of rotation theta p to the second principal direction is 67.5 degrees. Okay. And then let me draw the stress element here. So right now, x has been rotated to x prime, and y to y prime, and in the x prime directions, and we have the normal stress and 341, and in y prime direction we have the normal stress and 59. Okay, so that is symmetric. That should be in this way, 341, 59. Okay, so here you have two options to present your calculations for principal stresses and principal directions. And here we have two values of the principal directions. This one in counterclockwise, and this one in clockwise. And doesn't matter which option, this option or this option to go, you can see the distribution of the principal stresses, and 341 pointing in such a sense. If my drawing is not so perfect, but here the 341 is in this sense, and 59 is in this sense. Okay, in this sense. And from here you can see, if my drawing is perfect, basically the two figures, the two options will give you the same distributions of the principal stresses. Okay, so here, if you take these options or you take this option, that will give you the same result. And in terms of the test, and I would ask you to present two values of the principal stresses. Sorry, the two values of the principal directions. Okay. So that is for this example here, and then similar example can be applied to this one, and then here is the detailed calculation, and we have done is this example here, and those are the detailed calculation, and probably you can exercise for yourself by this one here. Okay. And So maybe I can base upon this information to draw it. So sigma 1, so for this case, we first determine the sigma p1 is counterclockwise. So basically, this is the theta p1 counterclockwise, 22.5 degrees. Okay, so in that sense, this is x prime, this is y prime. Okay, so here sigma p1 is here, so this is our x prime and 59, 0, and this is our y prime 341, 0. Okay, so here x prime is 59, so this is 59. Okay, y prime, this is 341. Okay, so that should be for this case. Okay, and now for theta p2, 65. So let me use the different color here. So that's 65. So that is this one. Okay, 65, 67.5. So clockwise, 67.5 degrees. Okay, so the stress element will be like this one here. And now for this case, this is x prime, this is y prime. So if you choose this sense, then in this case, the x will move to x prime, okay, and use color, okay. Y in this sense will move to y prime, okay. So x prime will be 341, 0. So here is 341, and then y prime is 59, 0. So in y prime, this is 59 here. Okay, so the same thing. If you look at the two stress element in space, you can see their distribution of the normal stress. 59 is in these directions, and 341 is in these directions. Okay, good. So that is the very quick exercise for your learning. So probably I keep the notes here. Okay, hopefully you print out that one and give yourself more exercise. And here we can also exercise to find the maximum shear stress and the orientation at which in which the maximum shear stress occurs. So for this case, again, we start from our given status, and the maximum shear stress, and again, is here. So this is, let me use the color. I don't want to use this one. So this is our maximum shear stress, okay, because that is basically labeled where that is a maximum, the value of the y coordinate, and that is a maximum shear stress here. So basically here, the north pole and south pole institute the point of the interest on the Mohr circle we want to transform. So let me connect this north pole to the south pole to form a diameter to which we want to transform here. Okay, so we have two options from the given x, y. If you would choose this orientation, so that means x will move to x prime and y will move to y prime here. And again, if you would choose this option, so let me say that's a 2 theta 1. Okay, if you choose these options, then x prime will have the coordinate and the average is 200. Okay, so that is 200, and the y, the radius is 141. So y prime is 200 and 141. Okay, and then you label this point x is in the lower quadrant. So these things have this. Then y point is on the upper quadrant. So the second component have this sense like this one here. Okay, so now what is 2 theta 1? Earlier from the previous example, we calculated this is 45 degrees. So therefore, can you see 2 theta 1 equal to 45 degrees? So that means the theta s1 equal to 22.5 degrees, and then here we choose this sense, so that is this orientation. So let me draw it. So here that is the 22.5 degrees, okay, and in counterclockwise orientation, so that is the stress element here, and x prime, y prime. Okay, so now in x prime, the stress is given by this one. The first coordinate is 200 normal stress. The second magnitude is 141. So we know the shear stress is 141. Now I want to determine the direction. From here you can see the direction is in the tendency to rotate the block. The tendency to rotate the block in that direction. So that in 141, so it should be like this. In this sense, we have a tendency to rotate this block in this sense, that fitting into this direction. Okay, now we determine the y prime. Y prime, the first coordinate is 200. Then the second coordinate is the magnitude of the strain stress, 141. The direction is determined by such that it has a tendency to rotate the block in that sense, so that must be in that direction. Okay, so that is the first option for you to choose from. And then let me erase these calculations and performing the second options for calculation here. Okay, and again, let me form the diameter to which we interested, to which we want to transform. Okay, now I'm present the second options. The second option, this is our previous option, 2 theta s1. Okay, the second option is this. If you would choose 2 theta s2 in such that this is our y point, x point will move to here, this is our x prime, and why do this orientation follow the same sense? So y will move to y prime here. So x prime equal to 200 and 141, and the sense is this. Y is 200, 141. The sense is this. Okay, again, the y prime located on the upper lower quadrant, so we take this sense, and this upper quadrant we take this sense. Okay. So now the 2 theta s2, earlier we calculated this is 45 degrees, so therefore 2 theta 2 will be equal to 180 degrees and minus 45 degrees, because this angle is 45 degrees we determined earlier, so that is 135 degrees. So therefore theta s2 equal to 135 degrees divided by 2 equal to 67.5 degrees, and the sense is this. Okay, so now we draw that one here. So the theta s2 equal to 67.5 degrees in the sense clockwise. So clockwise. Okay, so this is our stress element. So here this is our x prime and this is our y prime. So now we determine the element. So in x prime we have the stress, normal stress is 200, and strain stress magnitude 141. So that's the magnitude. The sense is in such a way rotate in the block in clockwise way. So that should be in this way. Okay. Again, 141 on the new x prime plane have a tendency to rotate the stress element in this sense. So that this one we place here, you can see that is a tendency to rotate in that sense. Okay, so we don't need this one. So now for y prime, so y prime, this is a 200. We have 200 normal stress, and again the second component is strain stress. The strain stress has a magnitude 141. Okay, 141, and then 141 has a sense to rotate the element in that in this way, so that must be in that direction. So 141. Okay, so that is the either option. You have two options to choose to go for finding the maximum stress, and either these orientations 20 or in this blue one. Okay, either option will give you the same sense of the distribution of the stress element here. Okay, the same sense of the distribution of the stress components. Okay, so that is for this simple example, and again you can exercise for this example. Let me skip the detail, but here provide you the detailed calculation, and hopefully you can reproduce the example for this case and similar to this one here. Okay. Right now we have gone through how to apply the Mohr circles to determine the principal stresses, principal orientations, and apply the Mohr circles to determine the maximum stress and in the orientation which the maximum stress occurs. Sorry, the two topics. Now we want to go to the last one and do apply the Mohr circle for determining the transformed stress here. Okay. So again, here the XY diameter indicate the given status of the stress, and then here, for example, here we have this one. For example, if say we want to determine the status of the stress at any arbitrary angle, say theta, okay, for this demonstration, theta is the angle you pick, or I as the test designers, I designed a value, and in say for this illustration clockwise. Okay, so once we assign or we select the orientation to which we want to transform the stress, then on the Mohr circle you simply rotate the given diameter in the same sense. For this case here is this clockwise direction, so you choose to rotate x will move to x prime, y will move to y prime in the same sense, okay, in the same sense here. And by how much? Here we are given is theta, and here on the Mohr circle you transform by 2 theta. So once you determine the x prime, y prime point, then the remaining is for you to determine the coordinates of the x prime, y prime that were representing the stress, the transformed stress. Okay, again, once you determine the diameter to which you want to transform per the given information, the remaining is simply locate the coordinates of the x prime, y prime, and that will be the answer. So we can look at the example here. We continue from our previous example here. We are given this example. Okay, so for example, here I want to exercise to transform by, say, arbitrarily 60 degrees. Okay, so here the x and y are the points that describing the given status of the stress. Okay, that is propagated from our previous exercise just about half hour ago. So now we're given the theta 60 degrees, so and that is in the sense counterclockwise in this example. So in the same sense counterclockwise, and by how much? 2 times of theta, so that is 2 times 60 equal to 120 degrees. So you take you measure the 60 degrees, and then from here you get this one. So that is a sense of rotation. In such sense, you simply rotate this diameter in this sense, x will to x prime, and y rotating in that sense to y prime. So now I want to show you how to determine the coordinate of x prime, the coordinate of y prime. Okay. So here from previous example here, we know this is 45 degrees, and now this is 120 degrees. So basically here that this angle should be how much? 180 degrees minus 45 and minus 120. So that should be 25 degrees. Hopefully, yes. Let me double check. So this one is 60. Oops. I think I made a mistake here. This should be, I think this one should be 15 degrees, right? Okay, so whatever. So that should be 15 degrees. Okay, so now for this triangle here, this is 15 degrees. So let me pick out this triangle for us to determine the coordinates here. Okay, so we know the radius. This side is our radius. Okay, radius equal to 141 if you remember. So let me highlight here. Larger will be easier for us to determine here. So r equal to 141, and we determine this is 15 degrees. Good. Okay. So in this case, from here, this side will be equal to r times cosine 15 degrees, And let me punch the calculators quickly. 141 times cosine 15 equal to 136.2. Okay, and this side is r times sine 15 degrees equal to 141 times sine 15 equal to 36.5. Okay, so let me get rid of unnecessary information to clean up the things here. Okay, so basically let me translate the informations. So basically here, this side from here is 36.5, and from here that is 136.2. Okay, so now we want to determine the x coordinate. This coordinate is the horizontal coordinate, basically is this amount plus this amount. So basically this number equal to 136.2 plus average, so that is 363.2. Okay, and then the second coordinate here, that is given by this one, 36.5, easy. Okay, and then here the seems x prime located in the lower quadrant. So let me rewrite this one. It's 336.2 and 36.5, and the second coordinate has this kind of things. Let me label that one here. Okay, so under this case, let me draw it. And so basically here, once we transformed, and this is our x prime, this is our y prime here, and x prime has a coordinate, the first one 36.2, and this one is 36.5, so this is a 36.5. Okay, and you can repeat the similar way, and maybe you can utilize this triangle to determine y, but I can tell you for y here, basically this one is the same as this one, because the two triangles are symmetric, the same size. And then y, this one is the so this one is 36.5 here, and the sense is this one. Okay, and this one tell us the first coordinate here. This coordinate we can utilize is this. You can calculate basically that one, this one equal to 200 minus the same distance here. The distance basically from here to here, this distance is the same thing here. Okay, it's 136.2. Okay, and that one equal to 63.8. Okay, so basically y has the coordinate 63.8 and 36.5, and the sense is like this one. So y prime has this sense. Let me multiply 63.8, and then the sense is like this one here. Okay, so that is the transform stress for this problems, and a little bit messy, but I made a mistake in my slides preparations. But here that is the here, ignore this one because that should be 15 degrees. So that is the calculation for this one. Okay, and we can take a look at the kind of examples that prepared from our textbook. So basically those examples, two more examples, combine everything we kind of been through. Okay, so we are given the status of the stress. So the first one will build out the Mohr circle. So this is a center at 20. And then radius, you can determine the radius equal to sigma x minus sigma y divided by 2 square plus tau x y square. This calculation will give you 50 minus 10 divided by 2 square plus 40 square equal to 50. Okay, so this is the radius. So with the center with radius, you build up this circle. For this example, this circle basically cross the vertical line, so basically it occupies 4 quadrants. It's okay. So now we determine the x point. X point is the status of on this plane. So the first coordinate is from the normal stress. The second coordinate is 40, okay, and the 40 has a sense by this, okay. So the x will be accordingly determined at here. This is 50 first coordinate, and 40 is this coordinate here, okay. So this is an x point, this is a y point, and then from this point we want to determine the principal plane and principal stresses. The principal plane and principal stresses, let me erase the unnecessary mark here. A and B are our principal stresses, and here this one is our maximum. Okay, the maximum is how much you can determine. The maximum is equal to let me see. So from here, this is our radius 50, okay, and then this number is 20, okay, and this number is 20. Basically 20 is determined by our center, so basically this is the 50 plus 20, this is 70, okay. And this one we can calculate. Basically B has a coordinate as minus 30 and 0, so minimum equal to minus 30. Okay, you simply observe the coordinates here, and minus, that means this minimum principal stress is compressive, and this one is the tensile. Okay, tensile. And the orientations, simply you can pick one direction. For example, you pick this direction, okay, so that means x in this direction move to x prime. Okay, so in that sense, let me call this 2 theta p1. So 2 theta p1 can be determined by this triangle here. This is normal, basically is the shaded triangle here, okay. For the shaded triangle, R here is 50, okay, and then this is 40. Let's pick up from here, okay. So that means from here you can take this sense. So this is our 2 theta p1. So if you took theta p1 in this case, the sine 2 theta p1 and equal to and 40 over 50. So from here you can determine the theta p1, that is arc sine of this, and divide by 2, okay. And then the maximum strain stress, let me erase everything here, and then let me redo the things. So the maximum strain stress is where the first one this is the north pole, this is the south pole, corresponding to here we have the maximum value here. So the maximum value equal to R equal to 50, okay. So now we make up this is the diameter to which we want to transform to. So for example, if you would choose these directions, so that directions, let me call the 2 theta s1, and in that sense x will move to x prime, okay. So from here you simply can determine 2s1. So earlier we determined 2 theta p1. So by looking at the graph here, 2 theta s1 plus 2 theta p1 equal to 90 degrees. So you don't need to, if you like, you can recalculate using whatever the triangle available to you. But by observing the graph, this relation come up naturally. So that is a quick way. So the magnitude of the maximum strain stress basically is equal to R, okay, equal to this one. The corresponding, the directions, that is theta s, and using this equation here. So that is a detailed calculation, and the sense of the drawing the block for your reference. This example from our textbook, so you can get more explanations from our textbook.